Hello everyone, I hope you're all doing well. This set of notes is going to cover sections 16.7 to 16.8. So we'll begin with weak bases. First, let's compare weak acid equilibria. Some generic weak acid plus water gives hydronium and its conjugate base. If you recall the equilibrium expression for Ka, A is for acids, it's going to be your products over reactants. And we only put in substances that have aqueous phase labels. So Ka is for acids, and we make hydronium. For bases, weak bases, they always form OH minus. We're going to use Kb. So if you take some generic base, some are neutral, some have charges, doesn't matter at this point, you can call it B, plus water gives, this is your base, every base has its conjugate acid, and in this case water is acting as the acid, so then hydroxide is its conjugate base. Anytime we're making hydroxide, that means we're dealing with a base. So we're going to write our Kb expression. B is for base. Same as we did with acids, it's your products over reactants. We don't include water because it's a liquid. So our weak bases are going to fall into two general categories. Neutral substances that contain nitrogen. Every once in a while a nitrogen compound will have a charge, but for now it'll be neutral and contain a nitrogen, like ammonia plus water produces hydroxide and ammonium ions. Here's your base, conjugate acid. Water is acting as the acid, hydroxide is the conjugate base. The other class of bases that you need to know about are your anions, things with negative charges, and these are going to be your conjugate bases of any weak acid. So the conjugate base of any weak acid will function as a weak base itself. For example, the acetate ion, you're familiar with acetate, CH3, CO2-. Now this is not the reaction in water. This is a neutralization reaction with sulfuric acid, but it illustrates how the acetate ion can accept a proton. It's your base, and acetic acid is your conjugate acid. So other examples of this could be carbonate. Let's do carbonate and water. Carbonate can react with a water molecule to form HCO3-, hydrogen carbonate, and hydroxide ions. We could take phosphate, for instance, very weak base. Put it in water and we get HPO4- 2 plus OH-. And the list goes on and on. All of these are conjugate bases of weak acids, and they will function as a base themselves. All right, so one of the main skills that we need to learn in this section is how do we calculate the pH given the Kb? So the first problem states that we want to calculate the pH of a weak base, methylamine, given its Kb. Now in section 16.6, we calculated the pH of a weak acid solution given the Ka. This is very similar. There's going to be one more step, but it's really not that bad. So just like we did before, we're going to write a generic reaction of our base. Then now it's in water. It's not a reaction with some other acid. It's just in water. every time write the reaction of the acid or base in water. You get the conjugate base, conjugate acid, and the hydroxide ion. We're going to set up our ice table or the rice box, reaction, initial, change, equilibrium. We're going to put in our initial concentration. Who cares about water? Products are 0. Remember, I'm plugging in molarities. Just to reiterate, BCA table uses moles. The rice box uses molarity. Okay, so we don't know how much of the base is going to ionize. That's why we use the X that we solve for. So 0.6 minus X, X, and X. Set up your rice box, write your equilibrium expression. So it's going to be products over reactants. And we can go ahead and plug our values from the equilibrium expression in. Sorry, from the equilibrium row. You can only plug into the equilibrium expression those things that are in the equilibrium row. So the Kb was given 4.4 times 10 to the minus 4th. That's going to be X times X on top. We put 0.6 on the bottom. So why am I not including X on the bottom? If you remember from the last time, we're going to assume that X is negligible. Assume X is very small compared to the initial concentration. So that means that X can be left out of the denominator, which means we're not going to have to worry about using the quadratic formula. Now, there are going to be times when you need to do this. When you get to college, you'll be doing it first without X, then you calculate your percent ionization. If the ionization is greater than 5%, you're going to have to go back and do the quadratic formula. However, we're going to keep things simple, and each time we solve for the pH, we're going to eliminate X from the denominator so we can avoid using the quadratic formula. So now we're going to solve for X. So X is going to be equal to, well, let's just write it all out. X is going to be 0.6 times 4.4 times 10 to the minus 4th. And if we take the square root of both sides, X is going to be equal to the square root. I'm going to plug this in your calculator. Take the square root of that. We get an X value of 0.0162 molar. So the next question is, what does this represent and what's our next step going to be? Well, X represents not only the conjugate acid concentration, the H+, but it also represents the concentration of the hydroxide ion at equilibrium. So, if we know the hydroxide ion concentration, I'm asked to find the pH, what should I do next? So in my first step, I solve for X. In my second step, I can find not directly go to the pH, but I can find the pOH, which is going to be the negative log of the hydroxide ion concentration, which is going to be negative log of 0.62, which is 1.79. And if I know the pH, the pOH, I can then find the pH, because if you recall, the pH plus the pOH equals 14. So then my pH will be 14 minus 1.79, and that equals 12.21. And that's how you find the pH of a weak base given the Kb. Alright, I'd like you to stop the video and try this one on your own. And when you come back, we'll go over it. Alright, I hope you were able to get the answer that's listed at the bottom, but let's quickly walk through this. We're going to find the pH of a 0.1 molar aqueous solution of ammonia. We know that ammonia is NH3, and we're given the Kb. Now, like I said before, it really doesn't matter. You could write out the reaction of ammonia with water, or you could just use B for any generic base, because these are all going to have a stoichiometry of 1 to 1, because they ionize in one step, or one step at a time, I should say, and we only care about the first ionization. So NH3 can only accept one proton, so we write the reaction with water. Plus a hydroxide ion. We set up a rice box. 0.1 molar. Who cares about water? 0, 0, minus x, plus x, plus x. 0.1 minus x, and x. So we write our equilibrium expression. Kb is going to be to your H plus times your OH minus. Divide that by the initial concentration of the base. So we plug in what we know. 0.1. When you solve for x, you're going to get the square root of 0.1 times 1.77 times 10 to the negative fifth. And we plug this into my calculator. 0.1 times 1.77 negative fifth, and then we take the square root of that, and we get an x value of 0.00133 molar, and that represents the concentration of the hydroxide ion. So that was step 1. Step 2, if you recall from the last example, we're going to have to find the pOH first. Take the negative log of the hydroxide ion concentration that you just found. And you get the pOH of 2.88. Next step, we can find the pH by taking 14 minus the pOH that we just found. We get 11.12. Alright, so if you notice, our pH, our final pH should have 3 sig figs, because our initial concentration had 3 sig figs. That's sort of just a side note if you want to be a stickler for sig figs. So remember, it's the number of decimal places after the values in the ones place. That's how we do sig figs on a logarithmic scale here. All right, the next problem is calculating the KB from the pH. So we just learned how to get the pH from the KB. We just took the KB and used it to find the pH. Now we're going to use the pH and find the KB. So it's going to be a very similar process. First step, let's write our reaction. So we have a weak base, we know the pH, we want to find the KB, and we know the initial concentration. So take our base, this water, this pH plus, no H minus. You can set up your rice box. We can write our KB expression. Okay, and we can plug everything in. We can use our simplifying approximation, or we can leave it there, because the last time we used the last time we used the pH to find the Ka, we didn't need the simplifying approximation. Why? Because there was a piece of information that gave us the x value, which eliminated the need to use the quadratic formula. So what piece of information is going to lead us to our x value? Well, you're given a pH. Is that the pH is 9.67. So the pH is 9.67, and I can find the pOH, which is going to be 14 minus 9.67, which is 4.33. And if I know the pOH, I can find the OH minus concentration, because the OH minus is 10 to the minus pOH. So 10 to the minus 4.33. That equals 0.00000468. That's 4.68 times 10 to the negative fifth. And that is my x value, which I can use to plug in to my equilibrium expression and solve for Kb. So let's do that now. Again, we don't need to use the simplifying approximation on the denominator because we don't need to use the quadratic formula when we know x. You plug all that into your calculator and you get 2.2 times 10 to the negative eighth. I'd like you to pause the video and give this next one a try on your own. When you come back, we'll go over it. Okay, so in exercise 14, you're asked to find the Kb given the concentration and the pH of a weak base, which is codeine. So let's just call this B to make life simple. We have a weak base in water, get the conjugate acid and hydroxide ion concentration. We know that the concentration was 5 times 10 to the minus third molar. 5.0 cares about water. 0, 0 minus x. We fill in our rice box. We write our equilibrium expression. Right, and we plug in what we know. So we're looking for the KB. It's going to be x squared over 5.0 times 10 to the minus third minus x. Alright, so as long as we can find x, we can find our KB. So from the last problem, we used the pH to find x. So if the pH is 9.95, then my pOH is going to be 14 minus 9.95. And that's a pOH of 4.05. And once we know the pOH, we can find the hydroxide ion concentration, because that is 10 to the minus pOH. So we'll plug that into the calculator. 10 caret negative 4.05. And we get 8.91 times 10 to the negative fifth molar. And that is your x value. So now we can plug that in to our KB expression. And when we do this, we get a KB value of 1.62 times 10 to the minus 6. All right, moving on to section 16.8. This is a very short section. We're just examining the relationship between Ka and Kb. We learned how to calculate them both, Ka in 16.6 and Kb in 16.7. So these are just your acid and base dissociation constants. There's one important equation we're going to be using. Ka times Kb equals 1 times 10 to the negative 14th. We also are going to need to know how to solve for the pKa, which is just the negative log of the Ka, and the pKb, which is the negative log of the Kb. And the final equation is the pKa plus the pKb equals 14. That's it. So let's just look at how we might have to use these equations. Exercise 15 says, use the following Ka constant to answer the questions below. So we're given a Ka for HCN, it's 4.9 times 10 to the negative 10th, and it wants to know the pKa. Well, what equation can I use? If I know the Ka and I want to find the pKa, pKa is the negative log of your Ka, so just plug it in. And you get 9.31. And finally, for part B, it says what is the Kb for KCN minus, the conjugate base? Well, if I know Ka and I want to find Kb, look at the equations above. Which equation could I use to find Kb knowing the Ka? We can use the one that tells us that Ka times Kb equals 1 times 10 to the negative 14th. So if we rearrange the equation, Kb will be 1 times 10 to the negative 14th over the Ka value, which was 4.9 times 10 to the negative 10. And you plug that in, and you get 2.04 times 10 to the negative 5th. And that's it. It's pretty straightforward. You're usually given all variables except one and asked to solve for a single variable.